Hi, I am Selva and welcome to my YouTube channel. In this one, we will try to understand everything about feature scaling techniques. We will cover a very important or very costly mistake that people normally make, very commonly make. It's difficult to trace and it can prove very costly when you are building your machine learning models. Let's try to understand that completely. Now, certain machine learning algorithms such as neural networks, k nearest neighbors, these kind of algorithms will not work well if the features are of different scales. For example, what I mean by that is, say you have a data set that contains, say, the age as one of the features and say the salary as one of the features, age and salary. The value of age can go from say 1 to 100 or more than that slightly possible, right? Whereas salary typically goes from say 0 to all the way to $1 million or even more. Now these two columns can be of completely different scales. When you pass this data as it is to a machine learning model, this machine learning model such as neural networks or k nearest neighbors, if you do this, this will not work well. It will not train well. So it is essential for us to scale these variables to come to a similar scale before using these algorithms. That is one reason. Another reason is for algorithms such as linear regression. For these kind of algorithms, in order for you to compare the importance of those features, you need to scale those variables to understand the impact. Otherwise, you cannot really compare how important the various features are. So that is one other reason that we want to use feature scaling. Now, when it comes to feature scaling, typically the three most common techniques are all these three. One is the normalization, which is min-max scaling. The second is the standardization scaling. Third is the robust scaling. All right, we will try to understand all these three techniques. We will try to understand the mistake that people normally commit and how to avoid that. So the first technique is normalization, also called as min-max scaling. What we want to do here is, say you have a variable called age. Let's say you have the age variable. The values vary from 0 to 100. Okay, so you have 15 here, you have 55 here, you have 45 here, so on and so forth. You have different values. So you have this age column. We are going to scale this in such a way that these values are going to vary between 0 to 1, or you could set your upper and lower bounds. This could be between 0 to 1, or it could be based on say 0 to 10 or 1 to -1 to +1, like that. Now the most common way of scaling it is making it vary from 0 to 1, right? To do this, we simply apply this formula. For every row here, every data point here, we apply this formula where say you want to scale the value 15. To do this, we will subtract, so from 15, we will subtract the minimum value in this data. So from this data, say the minimum value was 0, and the maximum value was 100, let's say. Alright, the minimum is 0 and maximum is 100. From 15, you will subtract the minimum value, which is 0, and divided by the maximum value minus the minimum value. So 100 minus 0. So this will become 15 by 100, which is 0.15. In this case. So we will replace 15 by 0.15. Alright. Because we set it as 0 and 100, the minimum is 0 and maximum is 100, it became like, it was quite straightforward to convert 15 to 0.15. So this is what min-max scaling or normalization is. If you want to change the limits, right, say instead of making it vary between 0 and 1, you want to make it vary between -1 to +1, we apply this additional one more step to this. So you have computed the scaled values. On top of the scaled values, we will multiply. So we have -1 to +1, right? So max is +1 and minimum is -1. So this whole thing will become 2. The value is 2 plus the minimum value is -1, right? So if the scaled value was 0.15, xi scaled is 0.15, right? We multiply this with 2. Then add the minimum value, which is -1. So this would become 0.3 minus 1, which is -0.7, So this is how we scale this whole data. So this is normalization. Let's look at the next technique, which is standardization. So in standardization, we apply a different formula. So you have the data, you have age, you have the different values of the age data. It can be anything. It could be any numeric data, right? Now you have this data. To apply standardization, what we do is we compute the mean of the entire data. You compute the mean. So mean is computed how? You add up all these data and divide it by the number of values. That would be the average of this data. So every data point, say this was 15, this particular value was 15. From 15, we subtract the mean and divide by the standard deviation. We do this for all the data points, and that would give us the standardized value of this particular data set. Now there is no limit that this particular data should, the standardized data should lie between say -1 to +1 or 0 to 1, nothing like that. Typically it will be around 0. So on doing this effectively, on doing this scaling effectively, the mean of the scale data is going to become 0 and the standard deviation of the scale data is going to become 1, right? That is the result of this kind of feature scaling technique of doing standardization. So this is the second technique. The next one is robust scaling. Now robust scaling is why the word robust comes is, in the presence of outliers, robust scaling is a more preferable technique to use compared to the other two techniques. Now we have covered min-max, which is normalization, min-max, and standardization. We have covered both of these techniques. The next one we are going to cover is robust scaling. The word robust comes from the fact that this is resilient. It works really well in the presence of outliers or extreme values in the data. So what I mean by that, for example, let's say you have a numeric column. So you have a numeric column. The values of the numeric column typically varies between 0 to 100, let's say. Alright, let's imagine this particular feature X. This feature's value typically varies from 0 to 100. So you have the value 10 here, you have 5 here, you have 99 here, you have 7 here, so on and so forth. You have different values. Now one particular value or few particular values, the values are very, very large, say it is 10,000 or more than that. Right? Let's say you have the value 10,000 here. You have a value 10,000 here, you have 100,000 here, let's say. Right? You have a very large value, but most of the values in this data is between 0 to 100. Now in this case, if you try to apply min-max scaling on top of this, those values is very large, right? So in this case, the maximum value is 100,000. So this value will be transcoded as 1. The maximum value, if you apply the min-max formula, this will get transcoded as 1. Remember what's the formula? Xi minus Xmin divided by Xmax. Maybe this is not so visible. Xmax minus Xmin. Right? The max here is 100,000. The min is what? 0. Right? And Xi in this case is 100,000. This is 100k. And Xmin is 0. So this is 100k divided by 100k. So this value will become 1. This value will become 1. And the minimum most of the data here varies between 0 and 100, right? So most of the data will be limited to very small values of the range. So the range is between 0 to 1. The 1 corresponds to 100k, right? So bunch of the data will be between the values of 0 to, my guess it would be 0 to say 0.1, right? The data will get bunched up. That is, all the data points, most of the data points at least, will get cluttered up into a very small region. Suppose if this is the number scale from 0 to 1, most of the data, after applying min-max scaling, most of the data is going to get cluttered up in this very small range between 0 and 0.1, and the value 100,000 will be over here. Right? That's the problem when you apply min-max scaling, and this is something that you should avoid doing. This is the caveat. You should never use normalization. I have seen people using normalization, apply normalization before you use algorithms such as linear regression or neural networks, these kind of things. You should never do normalization. Standard scaling is better, but even better than using standard scaling is standard scaler is using the robust scaler, because in the formula of robust scaling you have a different approach. Instead of subtracting it, so in standard scaler you are subtracting the mean and divide by the standard deviation. Right here, instead of subtracting with mean, we are subtracting it with the median. Median is less prone to outliers compared to the mean. So in that sense, this is a very good choice. And we are dividing it with the IQR, which is nothing but the difference between the 75th percentile minus 25th percentile of the data, R. and this is the chunk where the majority of the data points are. Remember in box plots, when you construct a box plot, the box here represents the core region where the data is located. This could be the 25th, this is the Q1, this is Q1, which is 25th percentile, right, 25th percentile, and this is Q3, which is 75th percentile. This distance is nothing but IQR, isn't it? That IQR is what we are applying here, which makes it resilient to outliers. If you want to read more about it, there's a very nice blog written on this topic. I will paste the link. I'll provide the link in the description probably. Now, this is the link, proclassacademy.com/blog robust scalar outliers. So if you go here, they have a very nice representation of how robust scaling avoids this problem of having, when in the presence of outliers, robust scaling does a very good job. So that is explained very nicely in this particular blog. You might want to check it out. Nevertheless, we cover everything in this particular notebook. Let's see how to implement all the three techniques in Python. So first we will import the packages. Pandas, NumPy, warnings, we ignore the warnings, set some options, not important, it's optional. First step is to import the data. I will leave a link to the data. You can refer to this link in the GitHub repository. You can download this and then start using this. Now import this data set, and this is how it looks. So you have the different customer names, their credit score, and all this data is present here. Now let's scale the estimated salary column, which is present right over towards the end of this particular data set. So estimated salary is present. We want to do the scaling, feature scaling technique on this particular data, this particular column. Now to do it, I'm going to first introduce some extreme values, and then we will do the three different techniques. So to introduce the extreme values, I'm randomly picking up few rows. So these are the different row numbers where we are going to insert those extreme values. So select those rows, right? Those rows values we are multiplying by 3. So we are inflating the values present in these rows of the data set. After inflating it, we are storing those rows in the same places. All right. So if you do a box plot on top of this, you can see this box plot is giving us, these are the different rows that are coming out as outliers. So we have generated the outliers. Now we are going to do the scaling technique on top of this. Now on describing this, you can see the minimum value is this much. You have the maximum value quite high, isn't it? So, and the mean here is around $100,000. Maximum is almost 6 times than the mean. All right. So we seem to have outliers here. Let's now see how the data is distributed. So on this data set, we are creating some bins. So I'm creating some bins here and displaying how many counts of rows exist in each of these bins. So for values between 1 and 10,000, we have 508 entries in this data set. Between 10,000 and 2,000 values, we have 476 entries, so on and so forth. If you scroll down, after 20,000, so after 20,000 values, this range, there are very less number of observations that goes beyond that particular value. So these observations are probably the outliers that we have. So we have two people scoring, having this much salary in this range, and one person here, so on and so forth. All right. So the highest salary is probably this guy. This one person is present here, has a salary that lies between 540,000 and 550,000. All right. This is the distribution. So there are certain outliers present in the data. Now let's see how to apply the MinMaxScaler. Now, by the way, you should never do this. If you have to do this, I am just showing you how to do this. All right. You should never do this for when you have outliers in your data, and in that situation, you might not want to do this as a feature scaling technique. All right. Nevertheless, we will see how to do it. Now, in the absence of outliers, this is fine. This technique is still fine. Anyway, we will see how to do it. Now, MinMaxScaler I am importing from scikit-learn.preprocessing. Set the range of the features. This is the default, and we are setting it explicitly anyways. So it will go from 0 to 1. Now then apply scalar.fit transform, pass in the data, and that is going to give us the output. Now this output will vary between 0 and 1. All right. The transformation is done, and you can check here. The minimum value is 0, the maximum value is this much. On doing a box plot, this is the problem that we were talking about. On doing this, so the value is is ranging between 0 and 1, 0 and 1, and most of the data here, this is the chunk where most of the data, 50% of the data is present here, the chunk, the core data is present here, and this ranges I think between 0.25 somewhere over here, right? Within this range, most of the data is present here, and you can see the outlier, the extreme values are distributed over here, which is not at all good. We don't want to be in this situation. So this is why we need to avoid this kind of a scaling technique. The next technique is standardization. So you can do it either manually. You simply compute the mean, right? You compute the mean and standard deviation. Then once you compute it, from each value of estimated salary, from each value, subtract the mean and divide by the standard deviation, and that is the output data that you want. You can do it this way, or you can also use the standard scaler from scikit-learn.preprocessing, import standard scaler, then do a fit transform on top of that. Get the data, do a fit transform, and that will give you the result. Right? So the output is exactly the same as the previous manual approach. So this is standard scaler, as simple as that. In order to, okay, here we have the box plot on top of this. Again, look at this, how the data is distributed. This is a much better distribution compared to what we had got using MinMaxScaler. So the data here, if you look at this, this is the chunk of the data, right? It varies between, say, I would say this is around -1 to +1, 2 plus 1. A good chunk of the data is located here, and the outlier data points still are outliers, still are having extreme values around 4 plus. This is a healthy distribution, all right? Now, even better than this is the robust scaling. You can do robust scaling using the robust scaler. This is also present inside scikit-learn.preprocessing. Import robust scaler, then apply fit transform. You will still get the same, or you will get the output, not the same output, you will get the outputs. On looking at the box plot for this, this is an even more healthier distribution. Okay, in this one there is no evidence that this is healthier than standard scaler. This is similar to what we got in standard scaler. Previously in standard scaler it was varying between -1 to +1. The box here was varying between -1 to +1. Here it is I think varying between -0.5 to +0.5. Right, this range it is varying. The scale has shrunk a bit, and the extreme values is present right from 2 onwards, which is good. Now in the presence of very large outlier values, in this example that we are seeing right now, the outliers are not that large compared to the rest of the data. But in the presence of very large outliers, robust scaling is slightly more robust than standard scaler. So both of these approaches work well. You can use both of these approaches, but try to avoid the MinMaxScaler in order to scale your data before passing it as inputs for training your machine learning models. So that's it for now. See you in the next one. Bye.